ça et lui il me passe celui-ci.
Test. Good afternoon, everyone. Thank you for attending this workshop about standardizing nuclear infrastructure and specifically tackling the ground challenges to accelerate the deployment of SMRs. This workshop is brought to you by EGIS, a consulting, engineering, and operation company with more than 8 years experience in the nuclear infrastructure projects. So before we delve in presentation, I'll let the speakers present themselves. Sure.
Sébastien Reynaud, I am a geotechnical technical director of EGIS.
Silvano Erlicher, nuclear civil engineering director at EGIS.
Thank you. So today the nuclear industry faces a key challenge, which is basically how we can, for new power plant, have a standard design that is replicable and deployable all over the world. So this is where we come to speak about the standardization concept, which is in theory simple. Basically use the same design, save time and schedule on the engineering sequence, and thus accelerate the deployment. But in practice, it's not that simple because every site is different. So this is where we come to talk about siting, because before we talk about any technology, we need first to talk about the ground, the soil, the rock, the seismic context, and also the water, which are basically the main parameters that impact how these infrastructures can be built and how they will behave over time. So this is where we come to talk about siting, which is basically assessing and qualifying the site before construction. In addition to the environmental and regulatory aspects, this siting procedure brings together three main scientific domains, which are the geology, first analyzing the soil and the rock structure. Then we have the seismology, which basically analyzing the seismic context and the ground motion and the seismic hazard. And finally, we have the hydrology, where we focus on the water flow and the risk of flooding, which these three domains really have big impacts on the design of the foundations and on the design, seismic design of the structures, and also on even on how we anchor the safety systems. So the question that we ask today is, how can we keep the same design even if the ground below is not the same? So to tackle this question, we have two approaches which are complementary. First, we will focus on the ground improvement and soil reinforcement solutions, which help standardize the soil, let's say. And the second approach will be focusing on seismic bearings and also a new solution which is currently under development, which is a future solution, which is the meta foundations systems, which provide a way to standardize the structure. So I will leave.
First, I will talking about the ground improvement and soil reinforcement. After conducting the siting study, we want to know if it is possible to make the soil homogeneous and consistent under the SMR. And so we try to standardize for one or two condition soils. And for this, we identify three families of solution. The first family concerns the replacement or in situ soil treatment. The second family includes the improvement of soil mechanical properties, and the third family concerns the reinforcement of soil and putting the soil inclusions. The main effect of this solution are the improvement of bearing capacity, the reduction of absolute and differential settlement, and the liquefaction mitigation. First, for the family one, you talk about the a solution which is the load distribution slab. It is a slab which constitute under the foundation of the civil work, usually made in concrete with the low dosage of cement. We can put or not reinforcement, and this slab, this concrete slab, is generally implemented by the roller compacted concrete technique, like we can see this in the figure. The field of application historically used for gravity dams, and we have one nuclear power plant in France, one example, which is in the north of France, which is Gravelines. The nuclear plant is founded on this load distribution slab. The action is the distribution of the load, a significant reduction of differential settlement, and the limits are the flexible strengths, the close availability of the granular material, and the relative high cost. Another solution for the family one is the grain replacement. Concern a soil thickness about 5 to 20 meter, and consists to extracting the soil and replacing it by granular material with good characteristics. We can also replace the soil with concrete. The field of application, the rail and the road project, and certain industrial and nuclear project and civil engineering works, demanding on the soil thickness to be improved, and this solution is generally challenging in the economic level with the deep foundation solutions. The action, the substitution of soft soil layer, a reduction of absolute and differential settlement by removing the soft soil, and the limits are the close availability of the granular material, the depth of excavation and the depth of water level, and the possibility to make dry excavation. A third solution in family one is the in-situ soil treatment. It concerns soil thickness about 5 to 20 meter. It consists to excavate the soil and take it back and treat it, the soil with successive layer. The treatment consists of an addition of hydraulic blinders like cement, of lime or fly ash, and in certain cases a particle size corrector, notably for the silt. The field application, mainly the rail and road project for the earth work and driver works like digs. The action, an in-situ treatment of such soil layer by avoiding the addition of external material like the previous solution, a constitution of a very stiff layer with a Young modulus of about 2 to 5 GPa, depending on the nature of the soil, and a significant reduction of absolute and differential settlements. The limits are the same: the depth of the excavation and the depth of the depth of a temporary support, and the depth of the water level, like the previous. Now I will talk about the family 2, and I will present another soil improvement, the vibro compaction and the dynamic compaction. The vibro compaction consists to densify the soil with checking it with a vibrator probe, and the dynamic compaction consists in pounding the soil repeatedly and with a pounder with high energy. The field of application, historically the port facilities, polder, and certain nuclear building, namely with vibro compaction to liquefaction mitigation. This technique can be very cost effective, and the design for escort is relatively easy. Because we can we can have an equivalent improved soil approach. The action, the soil improvement in the mass, the settlement reduction, and the limits, the limited improvement in soil characteristics. The depths vary between about 10 meters for dynamic compaction and 20 and 30 for vibro compaction, and the usual service pressure about 50 to 100 GPa. Another solution for family 2 is the soil mixing. It consists in incorporating hydraulic binders to constitute a dense network of columns or trenches. And we improve in the soil by different techniques like cutter machine, piling machine, or trenching machine. The field of application is the industrial buildings or linear structure, and improvement the soil beyond the retaining wall or to mitigate liquefaction. The action, improvement of the global mechanical properties and settlement reductions. The limits, the depth varies between few meter to 30 meter or more, but there is an economic limit. This solution can have a relative high cost. The design for a square can be difficult to adopt an equivalent improved soil approach. The durability is a question because we put cement in the soil, and the safety provided by the local nuclear agency, which is variable depending on the country. The third family, and the last, is the ground reinforcement. It consists to put in the soil inclusion like pile or concrete or steel pile driving or diaphragm wall panels in regular mesh. The field of application is historically under a retaining wall or access ramps to a bridge or embankment under the highway or railway, the port platform. And for nuclear building, we have one example in France with a technical building in nuclear plant. I precise the pressure, the applied pressure of about 150 to 250 kPa. The action, transfer the loads in the depth below the soil layers, and so a global reduction of loads. The limit, this solution has a relatively high cost. Concerning the REX, the service pressure varies usually between 50 to 250 kPa, especially in soft soil. And the design for ESCORC, the state of the art is not completely completed, notably in France. The durability, the question, and the safety approval. So in conclusion, it is possible to standardize the soil with different ground improvement solutions, provided that this solution will be approved by the nuclear agency. This table shows the three families. The third column, the nature of the technique, then the depth of treatment, and the usual ECLS pressure. And taking into account that for the SMR, the service pressure is about 500 kPa, the most appropriate family seems to be the number one, but the other solution can be implemented by several technical checks, and notably the pressure that the soil can accept, the durability in case this is a regular question, and the seismic design. It's finished for my part.
Thank you, Sébastien. So in this second part, in a few slides, I will present to you some this topic, standardization, considering site seismicity variability. And I would like to present two approaches, one which is quite classical, I would say, and another one which is, I think, for the future. It's not ready today for application, but who knows. The first approach to get standardization, seismic isolation, seismic bearings. So this is the classical one, we could say. Under a given structure, it is possible to put a lot of seismic bearings, and they reduce the vibrations of the upper structure. This is the example of the ITER tokamak building. You can see here some other pictures, more in detail, with the seismic bearings. Some models we implemented in order to study, to do the design of this. So how does it work? We start from a given soil, and the building we wanted to design, we consider a design basis earthquake. This is the reference. The response of the building to this motion depends on the frequency of oscillation of the building. And so when everything is stiff into the building, like it is usual, and for a normal soil, I would say, the frequency of oscillation is quite high. And so also the building accelerations are high. But this is the reference situation. So we have to accept this. And in this way, we produce the standard design for a building like SMR or other nuclear buildings. If we consider a beyond design earthquake, so another seismicity more than the reference one, if we change nothing, we get the response like this. So you see the response is increased because it is proportional to the increase of the input. We cannot accept this because if we do this, we have to redesign everything. So it is no longer a standard design. So the alternative is to use seismic bearings here. They are soft. So actually they reduce the frequency of oscillation of the building, of the upper structure. And with lower frequency, we also have lower accelerations. So we are here at a level of oscillations comparable with this one, with the standard one. So here, this building can be identical to this one, and also all the equipment inside, a standard one. Okay, without isolations, fast oscillations, large accelerations, with isolation, okay. Here I show you some pictures with existing seismic isolations for buildings in France. Here, reactor Jules Horowitz. This is a finite element model for a Chinese nuclear power plant, and this is for a street project, also in France, not constructed at the end. But seismic bearings are stiff in the vertical direction. They are soft in the horizontal direction, not in the vertical one. It means that with the beyond design earthquake, this solution or this one are similar in the end. So there is a drawback for this solution. Vertical oscillations are not significantly reduced. And for this reason, I show you another approach, which is for the future. We call it meta foundations. We have two rafts, the upper structure, for instance, the newer building, the lower raft, columns, composite columns, steel concrete columns, separating the two rafts, and in the space in the middle of the columns, we put some big blocks of concrete which are connected with the upper raft and the lower one by springs, wire ropes. So they can oscillate like resonators in the three directions of the space, X, Y, but also the vertical direction with the same efficiency. This is the idea. We can see here the frequency response function of the upper building. So without meta foundation, big amplitude and big frequency, then due to the columns, we have some flexibility, and then the resonators, they reduce the amplitude of the oscillation of the upper part. So there is a phenomenon of anti-resonance due to these oscillating masses for both horizontal and also vertical directions. So if we apply this to a SMR, we consider a design basis earthquake with these characteristics. we perform the design of everything, structure and also equipment. Then we consider a particular site, for instance here in Italy, where seismicity is bigger. We have to compare this and this. Of course, if we live in this way, we have to redesign everything, so it is expensive and very long. But if we put under the building the meta foundation, maybe if we are able to tune this meta foundation in a good way, we obtain for the upper part the same vibrations than here. So a standard design. We performed these calculations for the Newark SMR given here. You can see into the picture here the acceleration of the center of gravity here of the upper part. Without meta foundations, we have very high accelerations with the beyond designed earthquake. But adding meta foundation, the accelerations reduces for X, Y, and Z for the 3 directions in the space, not only for the horizontal ones. And the decrease of oscillations is up to levels here, which are the ones of the design basis earthquake. So the ones of the standard design. It is possible, actually, in this way, for this solution for the future, okay, it is possible to get standardization in 3 directions of the space. In this way, of course, it is possible to standardize SMR building design or other nuclear buildings, not only SMR.
Yeah, so just to recap, so we say here that the standardization is possible, it's achievable. It's a matter of studying the different options that we have, either to work on the soil itself or in the seismic isolations. As you saw, there are multiple choices, and obviously we need to do a benchmark for each technology, which is the most relevant one for soil or structure isolation. So that would be all. And thank you for your attention, and we can have some questions maybe afterwards, just next to the workshop.